Hello class, so we're back once again, Chemistry 112, Chapter 15. I believe this is Lecture 5. We're going to continue on, talking about the magnitude of equilibrium constants. Alright, so let's take a look at a generic, well not a generic, let's take a look at an equation here. Alright, we're going to have carbon monoxide plus chlorine is going to go to COCO2, right? We can write Kc for this, correct? Products over reactants, right? Kc meaning molarity. So again, products raised to a stoichiometric coefficient over reactants. And at a temperature of 700 degrees, this reaction actually has a value of 4.56 times 10 to the 9. Okay? So, very large number. What does this actually mean? Well, if we take a look at our equation, if we have a very large number, what does that mean? We have a very large denominator, very large numerator and a small denominator, right? If we're going to get a large positive number here, we have a large numerator, a small denominator. So that means the Kc will be large. What does that mean for our chemical equation? That means that the equilibrium will be with the products. The equilibrium lies to the right, okay? So basically, the larger K, or I'll put it this way, this would apply to Kp also. If K is much larger than 1, then the equilibrium lies to the right, or is to the right, with the products, okay? Again, large numerator, what would that mean? More products. Small denominator, what does that mean? Less reactants. So again, the equilibrium lies to the right, right? On the other hand, I should let you see that, I guess. If K is very much less than 1, then the equilibrium is to the left. Sorry, chalk goofing up here as usual. With the reactants. Okay? That's what the value actually means, all right? So, whoops, I forgot the 1 here. Now, when I say less than 1, I'm not talking about a negative number, all right? We're not talking negative numbers, but like 0.01 or something, okay, or 0.001, right? It's not going to be negative. You're not going to end up with a negative Kc, okay? So this just means between 0 and 1, but less than 1. If it's less than 1, the equilibrium lies with the reactants. And let's see here, what do we got here? Let's take a quick look at an example. All right, hopefully I explain that so it makes sense. Let's take a look at practice exercise 15.3. It's pretty straightforward, okay? They give us this chemical reaction. We had this one on the board the other day. Okay, and then it says at a temperature of 298 Kelvin, Kp equals 794, and at a temperature of 700 Kelvin, Kp equals 55. Right, Kp equals 55 is what it says. And then it asks, is the formation of HI favored at 298 Kelvin or 700 Kelvin? So let me put it this way. At which temperature is the formation of HI favored, right? That's what they're asking, okay? Now we can just tell from looking at this, what did I say? The larger your K, C, or Kp, the more the products are favored, right? So at 298 Kelvin, Kp is 794. At 700 Kelvin, Kp is 55. So both of them favor the products. However, at temperature 298, Kp is much larger. So temperature of 298. Kelvin. Right? Again, I hope that's making sense, okay? And we can write out Kp for this, right? I'll just quick write it out. Again, it's pretty straightforward. Products over reactants. Partial pressure of HI, right? Raised to its stoichiometric coefficient, divided by partial pressure of H2, raised to its stoichiometric coefficient, partial pressure of I2 raised to its stoichiometric coefficient. So again, the larger the Kp, the more the products are favored, right? Again, if you have questions, I guess email me. Okay. Now we're going to look at the direction of the chemical equation in K. Our equilibrium constant, right? So as I said earlier, an equilibrium can be approached from either side, right? Products or reactants. All this is saying is that with a reversible chemical reaction, you can start out with reactants only, or you can start out with products only. Either way, you're going to reach a chemical equilibrium, right? We talked about that a little bit earlier. Nothing new there, right? We talked about that earlier. However, this part is new, okay? The equilibrium constant K again, Kc or Kp, whichever one. For the reverse reaction, is the reciprocal of the equilibrium constant for the forward reaction. Okay? So the equilibrium constant for the reverse reaction is the reciprocal of the equilibrium reaction for the forward reaction. All right, let's take a look at what this looks like. Let me look at an example, right? Let me look at an example, write that down, right? And take a look at this example. I'll give you a second there. We're going to consider this reaction, which we've already looked at. N2O4 gas goes reversibly to 2NO gas. Okay? All right, let's write Kc here for this thing. Was that Kc or Kp? Sorry, I can't tell what the printing on this is fading. Kc, let's take a look at Kc. So again, products, we're talking molarity here, products over reactants, right? So raised to stoichiometric coefficient, like thus, okay? So that's going that way, right? Now we can actually calculate this value out, right? We can calculate this out. And if you had the experiment and the data, at a temperature of 100 degrees Celsius, that's what you get. Now let's reverse this reaction. Two-way arrow, we can reverse it. Right, so I just reversed it, very straightforward. Let me write Kc for this one. Products over reactants. Raised to the stoichiometric coefficients. Okay, here's Kc for this one. Compare Kc to that one. So forward reaction and reverse reaction, what is this? This is just the reciprocal of that. So what's this value going to be? The reciprocal will be 1 divided by 0.212, and if you actually plug that in, you get 4.72. And if you were going from this way to this way, it'd be 1 divided by 4.72 would equal 0.212. Okay? So the point here is that you reverse the reaction, whichever way you go, the Kc for the other reaction is reciprocal of it, right? That's it. That's all it is. Again, I don't know. Look here, if this isn't making much sense, take a look at this and this. These two are the reciprocal of one another, all right? So thus your values will be the reciprocal. Hopefully, again, I explain that so you understand it. Again, if not, you're going to have to email me. Let's take a look at an example here, though. Let's take a look at example 15.4. Basically, this is a very straightforward problem. They give us this reaction. So N2 plus O2 goes reversibly to 2 nitrogen monoxide, right? And then they're going to tell us at a temperature of 25 degrees Celsius, Kc for this reaction is 1 times 10 to the minus 30, all right? And then they ask us, use this information to write the equilibrium constant expression and calculate the equilibrium constant for the reaction, for the reverse reaction, right? So we're gonna reverse this here and then figure out what Kc is. First of all, before I do that, again, let's examine what does this mean. So if I write Kc for this expression, right? Again, this is in the numerator, those are in the denominator. Well, since this is such a small number, that's gotta be really small. So the equilibrium is gonna lie with the reactants, okay? 1 times 10 to the minus 30. That's a really small number. You gotta put 29 zeros in front of that, okay? So the equilibrium lies strongly with the reactants, all right? Now I'm gonna reverse this equation. Okay, let's write out Kc, that's what it asks for. Again, products over reactants, products over reactants. Raised to the stoichiometric coefficient divided by the reactants, concentration of the reactants, raised to the stoichiometric coefficient, okay? So again, and we know from what we just talked about, what's this value gonna be? It's going to be the reciprocal of that. So it's going to be 1 divided by, like that. And what's going to happen here, if you just move this up into the numerator, then we get 1 times 10 to the 30. So in this case, we reversed our reaction, right? Our Kc is really large, meaning that this is a really, really large number, right? This is a really small number. Since we reversed our reaction, now the equilibrium lies with the products, okay? Again, I hope that's understandable. We're gonna skip part in our book. It's just kind of a little bit complicated. I'd rather not write it on the board. Pages 621 and 622, if you're following along the textbook, which I know you all are because I know that's what you all do. And that's sample exercise 15.5. We are not doing that, okay? We're not doing that. And now let's continue on.